Okay, so we're merging back into chapter 7. I don't know if you remember the last time that we were here was actually for exam 2 when we were doing applications of solving right triangles, and we thought that we would put on together solving all triangles with that. And so in your second exam, we combined some initial sections of 7 with that, which what we were seeing in chapter 2, because everything was about solving triangles. And so if you remember, the first 3 sections are law of sines, law of cosines. And so we're picking ourselves back up and coming to vectors. And there's some questions in here that will rely upon that knowledge, but most of them, it's just a brand new idea, and it's best taught in conjunction with 8. And so here we find ourselves with our first introduction to vectors. And so if we look at the definition, a vector is a physical quantity that has both magnitude and direction. Typical vector quantities include velocity, acceleration, and force. We use directional line segments to represent vector quantity. The length of the vector represents the magnitude, and the direction of the vector, indicated by the arrowhead, represents the direction of the quantity. And so if you just think about applying force, if I'm pushing at an angle or if I'm pushing straight on, the force is different, right? And the angle is different. And so that's what vectors are. There's lots of applications of them, and they rely heavily upon trig in order to do them well. You can get angles between them, which will get you a magnitude vector of if 2 forces are working together but acting on different angles. You can use your trig in order to figure out some things, and so that's why it's being brought up. And so we're going to go over some common notation. The core notation, although it's not used a lot, is defining a vector by its beginning and ending point. And for this case, O and P. So I'm looking right here at the OP vector. Now, we need to let you know that it is a vector. One way to do that is bold notation. The other way is a line over the top that has a directed arrow. So if you look at the 2 vectors right here, OP is going up. So it has a length, which they call the magnitude. So whatever the length is, that's the magnitude. So this has a magnitude of a certain length, right? And they'll give us that what that magnitude is. The vector PO has to have the exact same length because P and O haven't changed, but they're not the same vector. They're going in different directions. And so it really is important to know who's your initial point and who's your terminal point, because if they're different, then they can't be the same. So their magnitude's the same, right? That's what this is saying, but they're definitely different vectors. So 2 vectors are the same if and only if they have the same direction and same magnitude. Then they'll be the same vectors. And so this gets a little bit weird how this printed out. At first it confused me, so I just want to have you look at this bottom area here. What's happening is this box somehow got in the middle of the wording. So it says the sum of 2 vectors is also a vector. We use the parallelogram rule to find the sum of 2 geometric vectors, adding tail to tip. So let me, they'd like us to add a vector A with the vector B. The sum of A plus B is called the resultant vector. So what we're going to have is 2 vectors working together, and we're going to use what they're calling the parallelogram rule. So let me explain that. So let's suppose that A is a vector that looks like this, and B is a vector that looks like this. And let me make B a little bit longer so that we can see it as different than A. I mean, obviously it's different because it's not heading in the same direction, but I want it to have a different quantity. What they're talking about with the parallelogram rule is what we're going to do. Each of these has an initial point, right? They start at some point and they go out a certain distance. The length of that distance is the magnitude. And so if we're going to add these using the parallelogram rule, which is a really great way to look at it from an application point of view, let me start right here. And what you do is you draw A. So I'm going to do my best to draw the same direction and the same length. So this is A. Then I had B coming in here, and B was going up like this and a little bit longer. So there's B. Now the parallelogram rule says, well, draw a parallelogram. So I'm going to come in here in red and just do some dashed lines that ideally are headed in the same direction of B and the same length as B. And then this then should be the length of A. So this is another A and this is another B, somewhere out in a different part of the plane. Now those are actually A's and B's, right? So there's thousands, millions, an infinite number of representations of the same vector B. The one in blue is. This red dotted one is. If I draw a black one down here that has the exact same length and headed in the same direction, that's also B. So B can be anywhere in the plane, and I'll bring that up again later. We're choosing to put A and B together at their initial points. When you do, let me come in here and I'll use this black color. This black vector that goes across the diagonal is the resultant vector A plus B that they're talking about. Now, it would not have mattered if I put B on first and then put A on. So they're asking, is vector addition commutative? The answer is yes. It looks like they're saying no, and that freaked me out at first because the answer is yes, but then I realized that everything was being carried over this box. So if you picture this box that moved over to the right, then the yes would have been right next to the no. And yes, vector addition is commutative, which is great. What we'll find is vector addition is very algebraic in nature. So for every vector v, there is a vector of the same magnitude as v, but in the opposite direction. Well, of course, if this is v, then negative v is that vector that has the exact same magnitude. And that's what they're saying right here. Negative v is that vector. And so I might have you do it on the exam. It's definitely in the homework just from a visual standpoint. What they like to do is have you picture these things happening. So what you want to see out of this is that, and I'm going to come back up to here, is that the way we got the A plus B, it was very specific in the parallelogram nature. The other way to do addition, which may be more helpful here, is for us to go back to blue. And I'll draw the A to the best of my ability right down here with its initial point here. And the other way to do it is to put B right at the end and then go in the direction of B to actually do that top red line, and then this is the resultant vector A plus B. Notice what happened is I just got the upper part of that parallelogram. They like the parallelogram for different reasons, which you'll see later on, and that's why they're bringing it up. But this is a great way to do this next one, to realize that if you just keep stacking the vectors on the ends, then where you start to where you end up is the resultant vector of everything being applied. That's super necessary here when you have more than one vector. If they only had two, we could do it the same parallelogram way. So I'm going to focus here on this guy right here. So they're going to show us some vectors over here. You might be like, well, what's U, what's V, what's W? Well, they got them drawn here. So 2U, that's where I'd like to start. And thinking about that, let me start over here. So U seems to go through cutting the diagonal 2. So 2U would go 1, 2, 3, 4. So this is where I'm starting. In fact, I'm going to make that point really pronounced because this is where everything starts from, this red dot. And this is 2U. So 2U would go in the same direction as U, but be twice as long. That's all that happens with 2U, is it changes the magnitude and doubles it. Now, the negative 3V, think about that for a minute. The negative is going to turn it backwards. So V is headed to the right, but now it's going to be headed to the left. And now we got to go back a lot. So if we look at V, and I'll highlight V in yellow, if we look at negative 3V, let me come in here and put this one in yellow and see if that shows up okay. It's going to come along here, 1, 2, 3, a long ways, right? This was 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got to go one more. 15 places. Okay, so it ends right there at that arrowhead. 15 places because it's got to triple and go in the opposite direction. So somewhat doable. And then we got W. So W goes up 1, 2, 3, 4, 5 and only hits through one hex. Right? So where does my W have to end? So let me highlight W. I'll highlight W in green. Oops. Go back and go green. This is W right here. So if I go back and draw W from this point, let me count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I got to end up right there from the start to end. So this looks like it's W right here. So where is the resultant vector? The resultant vector, which I'll put in black, starts from the initial point that we started from and then travels all the way to the ending point. That's the resultant vector of 2u minus 3v plus w. Interesting, right? I really, on the exam, I really look at you just adding a couple vectors. I don't really do anything like this, but it's good practice in there. So we have a little bit of blank space here. So what's really important for me to point out to you is, let's suppose this is the coordinate axis system. And I'm going to draw a vector here in blue, which I'm going to call v. It doesn't matter where v is in the plane, as long as v has the same direction and the same magnitude. So that one's a little bit off direction-wise. So as long as you're drawing something that's headed in the same direction, that has the same magnitude, it's v. It doesn't matter where it starts and ends. All that matters is the length of it and the direction that it's heading. So a common thing to do in it, because it simplifies the work, is to move v to the origin. If we move v to the origin, then it ends up in a very, very specific place. If this is A and this is B, this has coordinates AB as its terminal point. Its initial point is known to be 0. So a vector with its initial point on the origin is called a position vector. We like things in their position vector form. A position vector u with its endpoint at the point AB is written as, I don't know if that's subtle, they have these little brackets that are triangular in shape. If you ever see that, that's denoting a vector that's initial points at the origin and its terminal point is at AB. So A is the horizontal component and B is the vertical component. And so why not just stick the thing right at the origin and do all your work from that? Geometrically, a vector is a directed line segment, whereas algebraically, it's an ordered pair. We like that. We like that ordered pair. The positive angle formed between the positive x-axis and the position vector is called the direction angle. So I kind of drew it small, but let me get in here and make it big. This is what they're referring to as the direction angle, and often noted as theta. So if that's the case, let me make v really big here. So if I have a vector v that ends up at AB, and this is theta, well, from trig, we know how to get those things. So from trig, if we knew the magnitude, well, how do we get the magnitude? Well, you know how to get the magnitude. The magnitude would be, let me highlight what the magnitude is. You've been prepped for this forever, since pre-algebra. You know how to get that magnitude. Nobody has to tell you, but we will. Remember, this has out A and up B. You got a right triangle. Of course, the magnitude of V, which is this absolute value symbol, so this line around a vector is the magnitude, is the square root of a squared plus b squared. Magnitude is always positive, never negative. But absolutely it's going to just be the square root of a squared plus b squared, because you know that that green length squared is a squared plus b squared, right? The hypotenuse squared is a squared plus b squared. So even our pre-algebra skills allow us to know what that magnitude is, but our trig skills allow us to know, oh, that means a is the magnitude times cosine theta, and b is the magnitude times sine theta. We know cosine theta is directed to x, and sine theta is directed to y. And so they're going to have us look at some things together. Sorry, I'm trying to make that small. And just really rely upon this. So there's another form as well. So they throw out all these forms, right? Here's some vector operations that if you add two vectors, it's as simple as adding their x components and their y components. If you multiply it by a number, everything gets adjusted by that number. A negative then would obviously change things to be negative. And so it's pretty easy to work with these things. But before they get too far into it, they switch the notation again. So they want to have all the notation out there. So they started out with saying, hey, if you can define a vector between its initial point and its terminal point. Better is to define it as its components, right, in its initial position, with A and B being its horizontal and vertical component. And then it's also done a lot with i's and j's. So I is not the imaginary number I, like it will be in chapter 9. So there's going to be an I in chapter, I said 9, but it might be 8. An I in chapter 8 that is the imaginary number. This I that has the little hat on it is understood to be the unit vector 1, 0. And j is 0, 1. And so we can define things in terms of these two components. But it's not earth-shattering. So if I had the vector 3, 2, I can rewrite that as 3i plus 2j. So you could be asking yourself, why so many? The answer really is because of ease of work. When we take things out of what I call the component form and put it into its ij form, everything becomes more algebraic. Everything matches what we would have done even as a pre-algebra student. So for example, with this ij form, hopefully you know what this means. When they say u is equal to negative I plus 2j, all they're saying is if I go over 1, if I go over 1 in the x direction, negative, and up 2 in the y direction, that is the terminal point for u. That is my vector u right there. Right there. I get that nice vector u. What's the vector v look like? The vector v looks like go over 1 and down 1, and there's your vector v, always from the origin. So the ij form is also a position vector. But here's what it does for us. It makes everything algebraic. So this can be very, very nice. It can seem overwhelming, I guess, at first, but we just want to take a step back. You saw a lot. Now look how nice it's going to be. So this is like in the homework 26 and 28. We'll look at both of these. And so as we look at what they want us to do, A would like us to calculate what 2u is. No problem. That is 2 times the position vector negative I plus 2j. What does it look like you should do? Looks like you should distribute and get negative 2i plus 4j. And guess what you are? You're done. You're 100% correct with that. How about B? B wants us to take the 2u and add to it 3v. Well, you'll get really good at this. What's 2u? Well, I just figured it out. It was negative 2i plus 4j, so I can rewrite that and put it in there. So I got that vector. I'm going to just put it in parentheses just to highlight which one it is. 3v. Well, we don't have to write anything. We can just triple everything. So we get 3i minus 3j. And then what do you think you do when you add these? Of course, you just add the i's and the i's to get I, and the j's and the j's to get j. And you're done. Just like that. Simple algebra allows us to add and subtract vectors because we've written it in a form that is really, really nice for us visually. It's matching what's happening here because this said, hey, in order to bump something up by a number, just bump up both components by a number. In order to add two things, just add their x components and their y components. We just did both of that. And then how about C for this problem? C wants us to do v minus 3u. So be careful. They want us to start out with v, which is I minus j, minus 3u. And so a couple ways you can handle that. You could distribute the minus 3 right away, or I'm just going to hold it off and do 3u, which would be negative 3i plus 6j. So what's I minus a negative 3i? Well, we know that that's 4i. What's negative j minus 6j? Well, that's minus 7j. Where did we practice with this? Pre-algebra and beginning algebra. That's it. All we need to do is recognize that we're really dealing with vectors, but we're handling it algebraically. So something very similar would happen with this, and once you can see that you'll get these all pretty quickly. So let me erase this because it's going over a little bit, and we'll come in here. They want us to do the same thing. So for part A, I'll do it in blue now. So for part A, I just need to double u. Now look what they have. They have u in its component form, right? Not its ij form. No problem. Stay in that same form. They just want us to practice with it, right? And these are two successive problems, so that you can see that their whole goal is to just get you familiar with the notation. My goal is to have you not be daunted. How about B? B wants us to take 2u, which is negative 4, comma, negative 2, and add to that 3v, which is negative 9, comma 6. Hopefully you're okay with me coming up with those really quickly. We need to add them. A negative 4 and a negative 9, that's negative 13. A negative 2 and a 6 is 4. Done. C. V minus 3u. So v, negative 3, comma 2, minus u. 3u. So that would be negative 6, comma, negative 3. So just taking a moment to make sure I tripled u okay, and I got the minus sign in between. So negative 3 minus a negative 6 is positive 3. 2 minus a negative 3 is positive 5. And we're finished. That nicely. And so that's what it all really comes down to. So here what they want us to do is, it says for the pair of vectors with angle theta between them, sketch the resultant. So we're just making sure that we can draw some things. So what would we do? We would draw u. So let me draw u. U has a magnitude of 8. And v is 20 degrees different. So we'll just name that as 20 degrees. And v is longer. It's 12. Okay. So we'll say v is 12. And then the resultant vector, let me come in here in red and remind you what we would do. We would draw the parallelogram, right? Trying to be parallel to that 12 guy and as long. And here's my 8, right? And so the resultant vector, and they just want you to have a visual, is this guy right here. Now the reason why they want the visual is for some force type of equations that actually still happen in this section. So there's a lot of things going on in this section. Okay. So as we just take a moment to breathe, what we've learned is how to write a vector, what it looks like in order to add a vector. And so now we need to use some of the principles that we found from before. So what we want to remind you of is that the magnitude of a vector is equal to the square root of a squared plus b squared, right? If that u was the vector AB. And then we also know that x is equal to a cosine theta and y is equal to a sine theta. Oh, apologize. That is not the right symbol to use, not a. But I should be saying the magnitude of u and magnitude of u. Okay, so where am I getting that? I'm getting that from here, right? But it just makes logical sense in this regard. So why am I bringing that up? Well, that's what we're going to need for this problem. For this problem, we have the vector -7, 24. So they're asking us to find the magnitude of it. So the magnitude is going to be equal to the square root of -7 squared plus 24 squared, which is equal to the square root of 49 plus 576, which is equal to the square root of 625, which you might know is 25. So this thing has magnitude 25. Now they want us to find the direction angle. So we have a choice. We could use either one of these direction angles. It is wiser to use the cosine though. And here's the reason why. Remember the bounds for cosine inverse of a value. It was between 0 and pi. Right? Remember that? It would go between 0 and pi, quadrant 1 and quadrant 2. So that will help us out more than anything else. So, but we got to take a look at where this angle is. So as we go to get the direction angle, theoretically you could use either. I like to use cosine. So what do I mean by use cosine? Here's what we know. We know that x is equal to the magnitude of u times cosine of this angle that I'm looking for. Well, we know x, that's -7. We know the magnitude, it's 25 cosine theta. So now we know cosine theta is equal to -7/25. Now, what is the inverse of cosine of -7/25? And I believe that they want it in degrees. I think everything that we're producing in the back of the book is degrees. So let's make sure I'm going to check and make sure I'm in degree mode. I am. And so we're going to take cosine inverse. Cosine inverse. Alright, I got to take, sorry, I'm saying this again, cosine inverse of -7 divided by 25. And I get 106.26. So theta is equal to 106.26. Now you have to ask yourself though, is that right? Because cosine inverse can only spit you in quadrants 1 and 2. Well, this is a second quadrant angle. Look at where you're going to have to look at this every time. Look at where -7/24 lies. It lies in the second quadrant. This is our angle. If it had lied in the third quadrant, we would need to get a 106.26 reference angle, right? We'd have to figure out the right reference angle and get the right value. But we're good. So the magnitude, 25, that was one of the questions. The direction angle, 106.26. And so they're just having us use our trig in order to figure this out. Find the magnitude of the horizontal and vertical components of V. If theta is the direction angle and the magnitude of V is 238. Okay, so that seemed a little bit strange to ask it that way, but that's the way they're asking it. So they're giving us the angle and the magnitude of the entire vector when they want to know the horizontal and vertical components. They use the word magnitude, I think, inappropriately there, but I mean, we need to know that that's what they might do, but they're looking for the horizontal and vertical components. They're looking for the x and the y, or the a and the b, as the case may be. So, in fact, that's what I should put here. They should be A and B if I'm going to call those A and B. So I'll do the same thing here. They're looking for A and B as soon as we find them. Well, no problem. We know A is the x component, and we know that cosine corresponds for x from chapter 2 of this course. So this is 238 cosine of 146.3. And this is 238 sine of 146.3 degrees. Okay, and so what do we get out of this? Well, we just run it through a calculator. 238 times cosine of 146.3, and we get -198. And 238 times sine of 146.3 and we get 132. Okay, those are both rounded, but they're very close to those values. And so what vector do we have? We have the vector negative 198, comma 132. Does that make sense? Yes, it's in the second quadrant if it has an angle of 146.3 degrees. So a vector, write each vector in the form AB. So this they're expecting us to be able to do without the use of a calculator. So let's go through and do it really quick. X is equal to the magnitude. So let me rewrite that. The magnitude of u cosine of 60 degrees, and y is equal to the magnitude of u. Well, and we know the magnitude of u. Why am I writing that? Sine of 60 degrees. Well, we know what the cosine of 60 degrees is. It's 1/2. If you don't know that right now by just seeing that, you have big problems going into future courses. Please memorize your special angles. So they want us to write it in the form of the component, and we can do that. What about here with an angle that we don't know? Well, here that might be realistic to come out. So what do we have? We have x is equal to 2 times the cosine of negative 140 degrees, and y is equal to 2 times the sine of negative 140 degrees. So we do 2 times the cosine of negative 140, and we get negative 1.532. I don't know how they'll want us to round. Just round it what you feel is appropriate, and I'll give you credit, right? It does not truly matter to me. And then 2 times the sine of that same negative 140. Whoops, I got a syntax error. Okay, 2 times the sine of negative 140. And we get negative 1.285, or so negative 1.28. If I go to the same level, 286. But it is negative. Now the double negatives make sense because that's what you're finding is this point right here and this point right here. Obviously they'll be in the first quadrant and in the fourth quadrant. Alright, I'm going to stop this video right here and do a second part because there is still a little bit of work to do in this 7.4 section just so the videos don't get overly long.